And we'll begin with radiation physics and radiobiology. You can see the slides, I hope.
Recording in progress.
All right. First things first, principles of radiation physics. Now, for under the section of X-ray production, there are 5 things that we need to efficiently produce X-rays. Now, notice the word efficiently, okay? Um, we really only need 3 things to produce X-rays, but in order to get the most out of our equipment, which already is pretty inefficient because of the randomness of how we generate this electromagnetic radiation, there are 2 other things that we do to help with our efficiency and improve image production. Now, the first thing that we have to have is a vacuum, because without the vacuum, then we have molecules of air that could get in the way of our stream of electrons moving their way from cathode to anode. So we have the glass envelope or the glass enclosure, and we pull all the air out of it. That gets rid of anything that could get in the way of our source of free electrons generated at our cathode. Um, then we need to be able to accelerate those electrons. They're already going to have a little bit of an attraction from the cathode to the anode end. What we want to do is accelerate them and increase their kinetic energy. The more energy our electrons have, the higher the energy of the X-rays that we'll produce. The focusing cup at the cathode end helps to focus that stream into a tight area of our target. The smaller the area that we hit on our target, the lower the amount of penumbra we have, the better recorded detail we're going to produce. And then the third thing, or the fifth thing, however you want to look at the list, is a means of rapid deceleration of those electrons. Getting that kinetic energy, slowing those electrons down, and causing them to release that kinetic energy in the form of electromagnetic energy. So starting with our source of free electrons, remember the electrons come. Yes, please type your name in the chat. Perfect. Uh, our source of free electrons is going to come from the filament. Of course, our MA controls the current that's going to flow through either the large wire or the small wire at the cathode. Whichever one we put the current through, that's the one that's going to heat up. Temperature goes up. The thoriated tungsten filament is going to begin to boil off those electrons through the process of thermionic emission. Filament gets hot, those electrons are now movable. And the focusing cup helps us keep those electrons closer together. Remember the law of electrostatics. Like charges are going to repel, unlike charges are going to attract. Well, we get all these negative charged electrons in that one small space. That little electron cloud is going to want to spread out away from the filament, but not too far, because again, the filament, that's where the electrons came from. They're going to want to try to go back to it, because now the filament is becoming a little bit positively charged with losing those electrons. But don't let me get too far into that, because I can go into that pretty deep. The massive size of the focusing cup and it having a negative charge causes those electrons to stay closer to that filament. This is what we refer to as that negative bias. Now, again, because of the electrostatic attraction from between the unlike charged cathode and anode, the electrons are naturally going to want to go towards the anode and towards the target. But that pull of electrostatic energy there is not enough to get into the range of kilovolts that we need in order to produce diagnostic x-rays. So we're going to help that along by adding a kV, which is going to accelerate those electrons, giving them a higher kinetic energy. And once they get across to our target, they'll undergo that transformation. Well, the kinetic energy will get it'll be changed into electromagnetic energy. Now, the X-rays and heat, the heat is going to be of an electromagnetic nature as well. Because there is no air in the vacuum, we're not talking about a convection type of heat that's going to come out. We're going to have heat that is going to come out in the form of infrared radiation. More than 99% of the energy we put into our generators to produce an X-ray is going to be converted to heat. Which brings us to the next section here, our target interactions. These are the interactions of the electrons in the electron stream that come from the cathode at the anode, at our target. Two types of radiation, or two types of X radiation will be produced here. We'll have Bremsstrahlung and characteristic. The greatest percentage of X-rays that are going to be produced during an exposure will be Bremsstrahlung in nature. Very small portion will be characteristic, and depending on the kV, we may have all Bremsstrahlung. So Bremsstrahlung in German, translating it directly to English, means braking radiation. And notice the spelling. This is braking, as in putting on the brakes or slowing down or stopping, not break, as in destroying. Okay. And the reason for this, of course, one, Röntgen was a German physicist, but two, what's actually happening here are these electrons that are coming from the cathode are interacting with the tungsten nuclei. And they don't directly hit the nucleus, obviously. Some of them might, but a great portion of them are only going to be affected by the nuclear field and that positive pull of that nucleus, which is going to cause them to turn around that nucleus. The sharper the turn, the more kinetic energy is given up, and we get a higher energy X-ray photon. With this incident X-ray, this incident electron here striking the nucleus, all of its kinetic energy is then converted to an X-ray. So it's going to have the maximum energy. Now, it's not the maximum kV we set, as we'll see when we talk about the X-ray circuit, but it will be close, depending on the type of generator we're using. Electrons that only make a small, slight turn around the nucleus are going to give up less kinetic energy. So they'll still have an abundance of kinetic energy that can be given up in a later interaction. This is also the reason why the majority of X-rays produced during an exposure are of the Bremsstrahlung type interaction. So with the change of energy and speed, the X-ray photon will be produced. Because the binding energy of tungsten K-shell electrons is approximately 69.5. If we use a KVP setting below 70, or below 69, 100% of the interactions that are going to occur here are going to be of the Bremsstrahlung type. Once we go above 69 kV, then 85% of the interactions will be Bremsstrahlung. The other 15% will be of the other type of radiation that we produce, which is characteristic. Now, characteristic X-rays and characteristic interactions, um, their energies are dependent on the binding energies of the electrons of the target material. Okay, so since we're using tungsten as our target material, the K shell for tungsten is 69.5. The L shell, which is further from the nucleus, has a lower binding energy, and as we go out sequentially, the energy and binding energies drop. Now, characteristic interactions are going to occur when an electron is knocked out of its orbit. So part of the kinetic energy for the incoming electron is transferred to that electron, and it leaves a space. Now, the characteristic X-ray is produced once one of these outer shell electrons falls down to fill the hole, because ultimately the atom wants to be at a normal energy state and have all the proper electrons commensurate with the number of protons in its nucleus. So outer shell electrons will drop down into higher energy uh, shells. Okay. Now, it's those X-rays that are emitted when an electron drops that we refer to as characteristic X-rays. So the process here, the projectile electron comes into the electron cloud at the target. If it gets one of the K shell electrons out of its orbit, then other electrons will drop into it. So if the electron coming in does not have an energy above 69.5, then we will have no characteristic X-ray production because none of the electrons will get bounced from their shell. Now, once that electron is displaced, we're going to have a cascade effect. So we're going to have an electron from an outer shell jump down into that shell closer to the nucleus. And then in this instance here, it shows an L drop to a K. Well, that leaves a space in the L. An M will drop to the L, an N will drop to an N, and an O will drop to an N. That's what they're referring to as cascade. We're going from an outer further away from the nucleus and then dropping down closer to the nucleus. That's the cascade. However, it does not have to be an L shell that fills the K. It could be an M shell, an N shell, or an O shell that drops down into that space. This is the reason why characteristic X-rays, on average, we say that they are of 69 keV. Characteristic X-rays in the diagnostic range are at 69 keV because the binding energy for an L shell is 12. The binding energy for the K shell is 69.5. So the characteristic X-ray that is emitted from that drop is 69.5 minus 12. Okay. So 69.5 minus 12 is 57.5, or right? 57.5? That's not 69. So when we get to an O shell, which has a binding energy of 0.01 or 0.03, 69.5 minus 0.03 is 69.97 or 69.47. I'm sorry. Right? So that's higher than if an L shell drops in. So what they do is they take an average because it could be any of the shells that drop in. Some will give us higher than 69, some will give us lower than 69. So they just say the characteristic X-ray energy is 69 keV. So again, the energy that's emitted here is the difference between the binding energy of whatever shell drops into place. And we're only thinking about the K shell because anything less than that, like the L shell being 12 keV, its binding energy. If the M shell, which is I think it's like 3, that gives us a 9 keV characteristic X-ray. That's of no use diagnostically, and more than likely it'll get absorbed by the filtration and never reach the patient. Uh, and then any of the others that occur are much, much lower in energy, and most of those aren't even likely to leave the X-ray uh, housing. So what we only concentrate on is the K shell characteristic interactions and all the different averages or the different possibilities of X-ray energies that could be. So once an X-ray is produced, there are some characteristics that we need to look over. Remember that an X-ray itself is a photon. We refer to them as photons, and a photon is defined as a discrete bundle of energy which has no mass and has no charge. Okay. Now, because it is uh, emitted in and moves through space in a sinusoidal wave pattern. Okay, so that's what that S curve is. There are some things that we need to look at as far as characteristics of waves. Um, there are 4 main characteristics, and one of them translates to a 5th. The one that we don't deal with the most is, of course, amplitude. Amplitude being the height of the wave from the X axis to the peak or the crest, or the X axis to the trough. Any one of those would be defined as amplitude. We don't look at that, um, so we don't consider it when we're talking about our X-ray beam. The other 4, however, we do. Frequency, wavelength, and velocity. Now, frequency and energy, the 4th characteristic here, uh, are directly related. You double the frequency, you double the energy, okay? And vice versa. Velocity is constant. All X-rays exist at the speed of light, or they do not exist. Or they exist with the velocity of the speed of light in a vacuum. So we don't ever talk about velocity either because it is the speed of light. That never changes. Frequency, wavelength, and energy are related, and that the frequency, of course, is the number of waves that pass a particular point over a period of time, measured in seconds for the most part. The unit, of course, being in hertz, number of cycles per second. Wavelength is the distance between any of the 2 points on a wave. So if we measure from this crest to the next subsequent crest, that would equate to a wavelength. As the frequency increases, the wavelength will get smaller. So we have an inversely proportional relationship between frequency and wavelength. And if frequency and energy are directly related, we have an inverse relationship between energy and wavelength as well. No worries, Miss Mireles. Oh, any questions up to this point? And remember, if you have questions, ask because I'm always happy to elaborate. Okay. All right. So let's move on to the X-ray beam and beam characteristics. There are two key words that we associate with our X-ray beam. That is quality and quantity. Quality referring to the energy of our X-rays and its penetrating ability. Okay. Quantity, of course, is the number of X ray photons in our exposure and defines the intensity of our beam. Now, a lot of, even as second year students, I find that we have a little bit of confusion between quality and intensity. When intensity is a quantity, it's a measurement of the number of X-rays. I know with in our everyday lives, when we use intensity, we're typically talking about an individual or a type of thing that was difficult to do. So when you say, well, that was an intense workout, it wasn't that um, in that we're talking about the amount of work that went into that workout. So intensity is in fact a quantity. And so that's important to remember. Now, with quality, we're looking at the distribution of the X-rays as a function of their energy. Remember, we have a heterogeneous beam, multiple levels of KeV that are going to be involved in an X-ray exposure. And so we'll deal with the KVP, filtration, and the target material. And all three of those things are going to influence how well the X-rays that we produce penetrate tissue. With our quantity, we're dealing with the number of X-ray photons in that beam during the exposure, which goes back to directly to the number of X-rays. I mean, the number of electrons that we uh, freed for our exposure during thermionic emission. So controlled by, directly affected by the MA. So the three different areas that we look at. Now remember, the X-rays are emitted in the tube and in the housing isotropically. So that's with equal intensity in all directions. So there's only a very, very small fraction that happen to make it through uh, the window and out the collimator housing. Um, very, very small fraction. So whenever we set 5, 10 mass, the numbers that we're dealing with regarding mass are very, very small, very, very tame compared to what's the numbers that are actually produced in our tube. Remember that an ampere of energy, or an ampere of current, is 6.3 times 10 to the 18 electron charges. That's 1 coulomb. Um, when we're dealing with milliamps, that's still 6.3 times 10 to the minus 15. Or sorry, times 10 to the 15, not minus 15, times 10 to the 15. So it's an astronomical number of uh, X-rays that are being generated when we make an exposure. So mass is it's a small quantity. Um, but what exits our collimator housing we refer to as the primary radiation or our primary beam. The X-rays that exit the patient are referred to as remnant radiation. Now, exit and remnant radiation is composed of uh, the X-rays that made it through the tissue, either through transmission or by scatter. These are the ones that we're typically going to try to harness for our images as well. So the first formula we look at in physics, in most cases, other than the wave formula or the electromagnetic wave formula, is the inverse square law. And the inverse square law basically states that the intensity of the beam will vary inversely with the square of the distance from the source of radiation. Okay, so when we increase our distance from our X-ray tube, the amount of radiation measured at a certain point will be less as the distance increases. Okay, but it's, if we double the distance, we don't double or cut the intensity in half. We actually cut it by a square of that. So um, we have the formula up here, I sub 1 over I sub 2, I, of course, standing for intensity, uh, over is equal to d sub 2 over d sub 1. Now, you can write this where I sub 2 is over I sub 1 as long as d sub 1 is over d sub 2. Just make sure that your subscripts, the ones and the twos for the inverse square law, are on the opposite side when you cross the equal. Okay, it doesn't matter how you set it up, as long as 1 crosses with 1 and 2 crosses with 2, you'll be fine in your calculation. Okay, I always set mine I sub 2 because that's the one that's typically that we're solving for, and I like my X to be on top. I don't want my X to be on the bottom, which is what it would be for here. So the math application, the exposure from an X-ray tube operated at 70 kV, 200 mass, is 4 milligray sub A at 90 centimeters. All right, so there's a bunch of numbers there. How do we know we want to use the inverse square law? Well, the first thing we're looking at here is the exposure from. Okay, so we know that this is going to be tied to the 4 milligray in air. Okay, we have a kV, we have a mass, we have an intensity or a unit, a measurement of exposure, and a distance. Okay, the key is to look at the question, which is, what will the exposure be? Okay, so just stop there. What will the exposure be tells us we're looking for an intensity, right? Since we're looking for an intensity, the inverse square law comes to mind. Now, it's solidified that it's the inverse square law because we're changing our distance. So here we have I and D. All right, so here's I sub 1 is 4, 90 cms is D sub 1, I sub 2 is what we're looking for, and 180 is D sub 2. So we plug those numbers into our formula, solve for X, and we'll get an answer. All right. Now, the quickest way for me on this without even using the formula is I look at it and I say 90 centimeters is where we start. And we're going to increase the distance to 180 centimeters. Well, that's 2 times the distance. I've doubled the distance. Now, this is the inverse square law. So if I double the distance, that's 2 over 1. The inverse of that is 1/2. Square that. 1 squared is 1 over 2 squared, which is 4. So 1/4 is the variance. Okay. Now take that 1/4 and multiply it times 4, and it gives me 1. So my answer is going to be 4 milligray in air. And if you run it through the formula, do the math, you'll find that that's exactly the way it goes. And when we double, triple, quadruple, or cut in half, uh, cut to a fourth, or cut to a third, those are easy to do in your head. You just, double the distance becomes 1/2, square becomes a fourth. Multiply that times your intensity. You're good. If you cut it in half or cut your distance to a quarter of what it is. That's 1 over 4. The inverse of that is 4 over 1 squared is 16. So your intensity is 16 times what it was originally. Those are easy. What we have difficulty doing is um, going from 40 inches to 72 inches. When it's not an even number, then you really need to use the formula and plug in those numbers. The fundamental properties of X-rays. And the most amazing thing to me about this particular slide is that these 10 things were put in place in Röntgen's original paper. So these things have not changed since the discovery and the publishing of his papers. X-rays are part of the electromagnetic spectrum. They are highly penetrating. They are invisible to the naked eye and travel at the speed of light. They do travel in straight lines as waves, so they go from one point A to point B directly. They cannot be curved or refracted, not on this planet. They have the characteristics of waves and particles. So in the characteristic of waves is they can travel through matter, but they can also interact with matter just like particles do. They do exist in a wide range of wavelengths and energies. A lot exist at the um, lower energy levels that do not fit in the diagnostic range, and there are many that exist higher than our diagnostic range. Because they can interact with matter, they can eject electrons from their orbits and ionize those atoms. The fact that they oscillate positive to negative electrically means that they don't have a charge. They're electrically neutral because they're constantly flipping polarity. Now remember, anytime we have, because of the laws of electrodynamics, anytime we have a moving particle or a moving charge, we generate a magnetic field. Okay, and it'll be emitted at 90 degrees. It'll fluctuate at 90 degrees to the path of travel. So if you have an X-ray coming at you like this, vertically, as it oscillates from positive to negative, there's a magnetic field that opens up on either side of its path of travel. And it goes to either side because positive, the magnetic field aligns one way, and then negative, the magnetic field lines the other way. So magnetically, they're neutral as well. But that's where the term electromagnetic radiation comes from, is because there are two sinusoidal wave patterns, one representing an electric and the other representing the magnetic. Um, X-rays can scatter. They can't be reflected. They can't be refracted, but they can travel in different directions once they've interacted with matter. Uh, Consequently, because they can ionize matter, as we learned in the target, anytime you knock an electron out of its orbit, the atom's going to try to remain electrically neutral. So another electron is going to fall in its place, producing secondary radiation. Now, it's different than characteristic because characteristic radiation involves the tungsten atom and starts with an electron, knocking an electron out. Secondary radiation, all of the different elements that make up the human body and the tissue vary in their molecular composition. So it's not one type of atom that we're interacting with. There's many different types. And because it starts with an X-ray coming into the tissue and knocking an electron out, the characteristic or that cascade effect produces secondary radiation. Remember, because what's coming out of the tube is our primary. What exits is the remnant, but secondary radiation is produced in the tissue anytime ionization occurs. So there are 5 interactions, and 3 of them happen in the diagnostic range, but only 2 of them really contribute greatly to image production. Okay. The first of which is the photoelectric effect or photoelectric absorption. This interaction occurs when we have an X ray enters the body and strikes a K shell electron or a tightly bound electron. Okay. It takes all of that initial photon's energy to knock that electron out of its orbit. So now this X-ray energy has been turned into kinetic energy minus the binding energy. All right. So now we don't have any X-rays. There's nothing. It's complete absorption of the incident X-ray. Without these interactions, we will not get an image. When I first start introducing these concepts to my first year students getting into the program, or actually in my intro class that I teach during the summer, we start off with light. Okay, so if you have light and you have a wall and you shine the light on it, there's going to be the light on the wall. But if you stick something in the way, then there's a shadow of that object because the light's not going through that object. It's the same thing with our x-rays. If all of our x-rays went through the tissue, the whole image receptor would be exposed and we would not see any of the structures. So, the photoelectric absorption is paramount in giving us the view of the anatomy. Without that shadow and absorption of those x-rays, we wouldn't produce images. The next interaction, let's continue with photoelectric absorption, okay? So the process, X-ray comes in, displaces an inner shell or tightly bound electron. All of its energy is needed to get that electron out of its orbit. And so the original X-ray is absorbed. Now, the secondary X-rays occur when an L shell or an M shell or an outer shell drops down into fill that space. The difference in the binding energies will result in a secondary X-ray. Okay, it's the same thing as what we call characteristic at the target, but again, characteristic X-rays are produced by an incoming electron. Secondary X-rays are produced by an incoming X-ray photon. The next interaction is the Compton effect or Compton scatter. These interactions occur with outer shell electrons or loosely bound electrons. Now, they do occur throughout the diagnostic range, but we typically have to have a moderate energy X-ray photon for Compton scatter to be produced. We're looking at about 20 to 40 keV here. This is what influences the technologist's radiation exposure, is the Compton effect and Compton scatter. Now, in this diagram here, I wish he would have used energy as opposed to wavelength. But he's using gamma here, and that signifies wavelength. Okay, so the wavelength of the incident X-ray is a specific amount, and the X-ray carotid here has a different wavelength. And so down here, he compares the wavelengths, right? So the incident wavelength is less than the scatter wavelength. Now, Wavelength and energy have an inverse relationship. So if this energy, I mean, if this wavelength is shorter than this one, that means this energy is higher than this one. Okay. So the reason for that is, of course, because some of that energy of that incident X-ray was needed to knock that electron out and to get it moving in a specific direction. Now, the angle of deflection here is dependent on how much of that energy is deposited into this electron. I think of a pool table when thinking about Compton interactions. When you use the cue ball as your incident X-ray and you strike a target ball, if you hit it flush, you hit it perfect, the cue ball's perfect, and it hits that target ball perfect, the target ball continues on in the same direction the cue ball was traveling with the same amount of approximately the same amount of energy. The cue ball stops, all the energy is transferred, but all of it's not transferred because some of it is given off with heat from the friction. Some of it is transformed into sound so that we can hear it clack. But get rid of all of those things. All the energy goes to that secondary ball. Now, if we hit the cue ball solid again, but don't hit the target solid, then it goes off at an angle, right? The less contact you make with the target ball, the steeper the angle will be, right? The more towards center you hit, the straighter that target ball is going to go. And of course, you go the opposite, the other way, then it goes off in a different direction. It's the same principle here. Let's see. Question here. Um, the due date for the safety examination is 2 weekends from now. So I believe it's the Saturday, uh, not this coming Saturday, but the next. Got to have 2 lectures before you take the exam. Now, that doesn't mean you can't take the exam when you're ready. I recommend you get both lectures before you try because the safety examination, those main ones, those are 30% of your grade. And so you want to do really well on those. The RadTech boot camp, go for it. Take it if you want to take it now, but I would hold off until at least the second lecture before trying to take the safety exam. Photoelectric absorption causes contrast. It definitely influences contrast in that the absorption of the material is going to determine how many x-rays will be transmitted. So I mean that's kind of a backwards way to look at it. Ultimately, we think of the x-rays that are transmitted uh, cause the contrast. But without photoelectric absorption, we're not going to see anything anyway. So yeah, differential absorption is more. That's Mosby. Me and Mosby go around and round about some things. Um, I think that's a backwards way to look at that. I, if you want to be super technical, you could argue that it was uh, what caused contrast, but ultimately it comes down to um, the X-rays that are transmitted, as well as the X-rays that are absorbed. It's differential absorption which does that. Photoelectric absorption contributes to the visibility and the photographic properties of our images, and we'll talk about that in image production for sure. If you're getting bounced, that's okay. Just crawl back in. We'll catch up. I am recording, so we'll be good. So our next slide here breaks down the Compton interactions for you. Outer shell loosely bound, electron gets ejected, and the photon has lower energy because of Some of it was given up to that electron, one, to get it out of its orbit, and two, to get it moving away from the atom itself. Photons change directions. They can interact with the IR. They can cause another interaction within the patient, or they could exit the body and strike an individual within the room. Um, Important note, these Compton scatter is capable of going in any direction. Okay. Coherent or Thomson or classical scatter is a low energy, typically less than 10 keV. Those interactions contribute to image fog. They're not useful in the diagnostic realm, and um, they travel mostly in a forward direction. Whereas Compton, the, it could go in any direction. Here's one slide that shows us Compton effect versus photoelectric effect and the effect of KV. Okay, I know as an instructor and as an educator, I've been to many conferences, and this is one conversation that always comes up on whether or not increasing KVP increases Compton scatter uh, or scatter production. And it's it's very gray in that area. You have to be very technically minded and open to a lot of things that you can't see. This slide, I think, sums it up for us. Now, um, in water, at about 26 kV, anything less than 26 kV, we're going to have very few Compton interactions. Okay. But as the KV does increase, we're going to get a greater percentage of Compton interactions. At the low energy range, we're going to have a lot of absorption. Okay. But as the KV goes up, we're going to have less absorption. And it's right at about 26 kV where we get across. And we're going to have a great increase in Compton interactions versus photoelectric interactions. We're going to have less absorption as our KV goes up. In bone, that level is at about 45 kV. So again, we're going to have let's see, that looks like about 0 to 18. At 0 to 18 kV, there's no Compton interactions. Right to about 20 or so, we're going to have no photoelectric interactions, and they'll start to go down. And again, at about 45, they'll cross, and we'll have much fewer photoelectric versus Compton. Now, this illustrates the increase of KV causing an increase in scatter production. But the key there is it's an increase in scatter production compared to photoelectric effect. Because in reality, as we increase our KV, we're increasing the amount of transmission and transmitted radiation, which means attenuation is going down. And attenuation is Compton and photoelectric. So, depending on how it's worded and how people are trying to uh, the meaning they're trying to convey, that's kind of a sketchy area. Now, this is the coherent scatter. This is the third interaction. Not as important in diagnostic because these energies are very low. They can contribute to image fog in cases where these interactions happen near the IR and happen to leave the body. All right. But this is what we refer to as Thomson, classical, or unmodified. And it's unmodified in the fact that the energy that goes in is the energy that comes out, and it's almost immediate. As soon as the incident X-ray interacts with the atom, it's released again in a different direction. Now, I said that coherent goes in all directions. If we have a plane down the center of this atom here at 90 degrees in relationship to the travel of our incident photon, scatter can go in any direction on this side of that axis line that I drew. Okay, even if it goes like this, nearly parallel, that is still considered a forward direction. Okay, so in any of these directions, Thomson, coherent, and classical goes in. Backscatter, as we may sometimes image, is produced by Compton scatter. It is not produced by coherent. So here, very low energies. The energy state of whatever it contacts, be it electron or nucleus, it just gets elevated and then is immediately released. Because no electrons are ejected from their orbits, it's non-ionizing in nature. So only two, Compton, photoelectric, are ionizing interactions. Coherent is not an ionizing interaction. So we talked about it, attenuation briefly just a second ago. Remember that attenuation is a reduction in the primary beam through interactions with tissue. The first thing that we look at regarding attenuation deals with the thickness of the body part. The thicker the body part, the more attenuation will occur. Thinner body parts allow for more X-rays to be transmitted. Um, Thicker patients are going to absorb more radiation. So here's you a chart for the effective atomic numbers. We know that bone absorbs more radiation than fat and air. Air is going to transmit more radiation than bone. And if you look at the chart, the higher the effective atomic number, the more likely we're going to have photoelectric absorption in that tissue. Any questions up to this point? Okay. Moving right along, we're making good time. So let's look at the biologic effects of radiation. All right. First thing we're going to talk about here are units of measurement. Okay. There's 4 different areas we're going to look at here. Okay. There are more than 4 units, but some of them overlap. So the first one we'll look at is the absorbed dose. Now, I know in some of your other courses, you may have been using traditional units and you may have had to convert traditional units to SI units. The registry is no longer testing traditional units. It's all SI. Okay, so that's all you need to worry about for these classes. I've tried my best to get through all of the exams and get rid of any traditional units in any of the questions. So if you find one or you see one, let me know so I can go back and fix it and then make any adjustments to the grades as needed. Okay, but right now I've gone, I think 4 or 5 uh, courses and haven't had any problems. But again, we're only doing SI units. So the absorbed dose unit is the amount of energy per unit mass absorbed by an irradiated object. So, simplest terms, it's the amount of radiation the patient's getting. Okay. This is going to be responsible for any biological damage, and the dose is used to indicate the amount of ionizing radiation a patient receives during a procedure. The unit is gray. Okay, that should be lowercase y, and it should have a subscript. The subscript is T, lowercase t, for tissue. So measured in gray, sub T for tissue. That's an important thing to add. The next unit is the dose equivalence. Okay, now this is uh, utilized so that we can compare absorbed doses between patients and types of radiation, because the dose equivalent factors in the fact that all radiation does not have the same energy transfer and biologic effect. So we factor in what's known as a weighting factor, radiation weighting factor. And so the dose equivalent, or the equivalent dose equivalent, flip them back and forth, it's okay, is the absorbed dose, which we just talked about, multiplied times the radiation weighting factor. And the weighting factor chart here, I would consolidate this if I were you, because you could see we have some that are repeating. There's a couple fives, there's a couple tens, and a couple 20s. We use this factor and multiply it times the absorbed dose so that we get a better idea of the biologic risk from the exposure. So let's say we have an absorbed dose. We have two separate patients. One has an absorbed dose of 5 gray in tissue of X-ray. The other has an absorbed dose of 5 gray in alpha particles. Okay, two different exposures, but they both have 5 gray in tissue. Okay, so um, using the radiation weighting factor, we take the 5 in X-ray, multiply it by the weighting factor of 1, we get 5 sieverts. If we do the same with the alpha particle, 5 on the absorbed dose times 20, now we've got 100 sieverts. So again, the alpha particle is going to have a higher energy, linear energy transfer. It will cause more biologic damage. All right. Even though the dose absorbed was the same as the one for X-ray, because of the radiation quality, we can understand the dose equivalence now. Okay. Now remember, it is in sieverts or millisieverts. Millisieverts is just a prefix. Now let's see. How come it increases at less than 100 MeV 20 and then drops back down? So greater than 100. Wait. I think that's why. Because that's greater than 100 keV to 2 MeV, and then it's greater than 2 MeV to 20 MeV, and then greater than 20 MeV. So it's actually not dropping back down. KeV, of course, is 100 kiloelectron volts to 2 mega electron volts. This is 2 mega electron volts to 20 mega electron volts, and then 20 mega electron volts. So it's actually not going back down. You see that, Mr. Norman? Oh, I'm sorry. I understand what you're saying now. Yes, the weighting factor is going to drop because now we're starting to exceed um, the absorption. So these are energies. Once we get to those energies, they're highly transmitting. The energy, well, it doesn't really say what energy it is either, does it? We're just going to have to assume that they're photons. Um, unless they're neutrons. And I would think that is going to be what these are. These are going to be the neutron values, and the neutron values are yeah, their energy's just too high. So yeah, too fast. Not in not in what we use. Now there are 20, I mean there are MEV X-rays. We don't generate any. Our machines aren't capable of doing so. No, diagnostic does not go that high. The diagnostic, well, the mechanical range for most diagnostic equipment is 30 to 150 keV. The diagnostic range for our x-rays and imaging is 50 to 125, maybe 130 keV. But there are x-rays that exist in the MEV range. Our machines don't do that. So the next unit we look at is exposure. Now, this is a measurement of radiation ionization in air because we can't measure ionizing radiation directly. We have to use a medium, and that medium is air. So this radiation quantity expresses the concentration of radiation delivered to a specific area. Um, the unit that they use to measure it in is coulombs per kilogram, but the other unit that can be used um, is air kerma, which is a little bit different um, because exposure is for an area. Kerma is going to be to a specific spot, smaller. It's not a big area; it's a smaller area. But that unit is also gray, sub A, subscript A, lowercase. Now, the effective dose, this is not the equivalent dose. This is where a lot of students get confused. Effective and equivalent aren't the same thing. Equivalent just matches the absorbed dose with the radiation factor. Okay. The effective dose uses the equivalent dose in addition to a tissue weighting factor. Okay. The effective dose is defined as the sum of the weighted equivalent doses for all irradiated tissues or organs. So that's the defining difference between effective dose and equivalent dose. Equivalent dose just makes the radiations equal by multiplying the absorbed dose by the weighting factor. The effective dose takes those two things and multiplies them times the tissue weighting factor. And here again, here's another slide that would be good, beneficial for you to consolidate. While there are lots of tissues here, there are only 1, 2, 3, 4 weighting factors here. Okay. So this again, just like the the equivalent dose or the dose equivalent is measured in sieverts. Air Kerma is the last unit. This is defined used to define radiation exposure or radiation delivered to a specific point. So it's very, very similar to exposure. Um, Again, the unit of measurement is the gray, sub A, because this indicates A. Remember, the sub T is tissue, and that's for the absorbed dose. The preferred unit is air kerma or gray over coulombs per kilogram. So this is another unit of exposure, right? And this chart sums them up for you, giving us the unit of measurement in the left column, what it is that we are expressing in the middle column, and then the unit that you may see. Now, moving into radiosensitivity and dose response relationships. Um, these are a combination of four different terms, four different descriptors, and they're paired. Like Spock, Star Trek. Anybody, any Trekkies? So we've got a blue term and a green term. All right. Threshold and non-threshold is the first pair. A threshold means that there has to be a certain specific amount of radiation that one is exposed to before there is a response to that exposure. Okay. Non threshold means that there is no safe amount. As soon as you start to be, as soon as you get exposure, then there's going to be a response. Okay. So threshold, non threshold. Threshold, you've got room. No, non threshold, there is no room for exposure. The second pair of terms are linear and nonlinear. Quite simple. If the line on the graph is straight, it's linear. If it's got any curve to it, it's nonlinear. So when we look at these three here, I'm going to go ahead and put a fourth one in just because that's fun. That way we get all four combinations here. All right. So there's number four. Number one, it starts at the origin of the graph. This point here, where the x-axis and the y-axis of the graph meet, is the origin. That is 0. 0x, 0y. As soon as we start to go over on the x, we start to go up on the y. Okay? As soon as we go up on the radiation dose received, we're going to start to see a response. That is non-threshold. The shape of the line, it's a straight line. So this is a non-threshold linear dose response. Okay. Number two, there's a certain amount of radiation we can get where no response is happening. Nothing is going on. Nothing is going on till we get here. And at this point, we start to see a response. This constitutes a threshold. There is a certain amount of radiation where there's no response. Okay. The shape of the graph, straight line, is linear. So number two is a threshold linear dose response. Number three, again, there's a certain amount of radiation that we have to hit before we start to see a response. That gives us a threshold. And because it is a curved line, it is nonlinear. And then four, the one that I added, starting at the origin, we're getting a response, but it is curved again. So it is nonlinear. That makes it a non-threshold, non-linear dose response. Very simple. Very, very simple. Only 4 possibilities, only 4 combinations. Moving into radiosensitivities, relative tissue radiosensitivities. You're very welcome, Mr. Vasquez. I'm glad that helped. Now, remember, as far as reproduction goes, somatic cells, these are all of the cells in the body with the exception of ova and sperm. Okay. They divide by mitosis. Ova, sperm, once they've combined, they divide by meiosis. Cells are radiosensitive during the late G2 gap and the mitosis M phase. They're least radiosensitive during the synthesis phase. And we go back into your radiobiology book to see when those occur. Linear energy transfer is a term that I used earlier when we were talking about the weighting factors and different radiation qualities. Linear energy transfer is the rate of energy from radiation that is transferred to soft tissue. Low LET, comprised of mostly X-ray and gamma rays. These are doses that are not excessive, primarily cause indirect damage to biologic tissues. And that damage can typically be reversed by repair enzymes contained within the cells. Radiation that is high LET, this consists of alpha particles, ions of heavy nuclei, and low energy neutrons. These can produce irreparable damage to the DNA because of the fact that they are so large, they can cause multiple breaks in the DNA strand that the enzymes are not going to be capable of repairing. As the LET of radiation increases, potential cause or the potential to cause a biologic response is going to go up as well. The relative biologic effectiveness, or the RBE, is the ability to produce a biologic response. A higher LET will ultimately yield a higher RBE. Ionizing radiation can change the molecular structure of the cell, which of course can impair and impede its ability to function properly. Somatic cell exposure can disrupt the ability of the cells to function. In reproductive cells, this can result in a mutation that's passed on to future generations. So, somatic cells in the exposed individual, we can have a disruption of those cells to function. They could die. It could also start cataractogenesis and cause other biologic effects to occur. In reproductive cells, those effects and damage they won't be visible in the exposed body. They will come later in future generations. Radiosensitivity. Our most common theory on damage that's done to a cell by radiation exposure comes from the direct effect or the indirect effect, or a direct hit theory or indirect hit theories. With direct effect, This is when the X-ray hits the DNA and causes damage. Okay. It's directly struck by an X-ray. An indirect effect, which is what most of our damage incurred during our exposures is from, is exposure to the X-ray photon and the water within the cell, within the cytoplasm. 80% of the cell is water. So it's more likely that we're going to hit that 80% than it is that we're going to hit part of that other 20. Okay. And so the majority of the damage that's going to occur will be from an indirect hit. So when the water is struck, it creates a free radical, and the free radical is what damages the DNA. Okay, so direct happens because of an X-ray hitting the DNA, and indirect is because of the free radical created by the X-ray. Target theory is another theory on radiosensitivity and damage. The idea here is that each cell has a master molecule that directs all the cell's activities. And so if the DNA of the target is damaged sufficiently by the radiation, the cell will die. Remember from the previous slide, DNA can be damaged by either direct or indirect effects. And that all interactions that occur within the cell are by chance. It's just like our interactions at our target. We don't really have a lot of control there. Now, the law of Burgonde and Tribundeau stated that radiosensitivity of the cells was directly proportional to their reproductive activity, meaning the more they reproduced, the more frequently they reproduced, the more likely they are going to be sensitive to exposure. And that they're inversely proportional to their degree of differentiation. So they're most sensitive to radiation when they're immature. An example of an immature cell would be a stem cell. It has not been defined in its function in the body yet, what kind of tissue it's going to be. Very, very immature, extremely sensitive to radiation. Again, because they are undifferentiated, they are sensitive, and especially during pregnancy, the embryo and the fetus, those cells are rapidly dividing. So they're extremely sensitive to radiation exposure. And the reason for that is, especially because they're rapidly dividing, there may not be enough time to go by or elapse for the enzymes to do their business and repair any damage done. And so we have a defect that goes on through the division, or the cell dies. So our radiosensitive and insensitive cells, and here's our little chart here. Basal cells of the skin. We're constantly shedding cells off of our skin. This is why skin cancer, quick to show up within your lifetime, happens when you're young as well, depending on the amount of sun exposure you get. Okay, this because those cells are rapidly dividing. Even though they're differentiated, they are skin cells, their reproductive cycle is quicker. Blood cells, especially lymphocytes and erythrocytes, intestinal crypt cells, and then our reproductive germ cells. Very radiosensitive. The radio insensitive, brain cells, muscle cells, highly specialized, as well as nerve cells, especially in adults. These are the least sensitive. Cell survival and recovery. The repair enzymes can repair and recover from sublethal doses of radiation. The lethal dose, of course, is used to describe the whole body dose that will be lethal to a population. There are two factors here. They're broken down in yellow. So the phrase LD 50-50 or 50-30 stands for the lethal dose that will kill 50% of the population within 30 days. So the asterisk represents the percentage of the population. That's the first number. The caret here represents the amount of time, the 30 days. So if this was LD 3050, that would be 30% of the population in 50 days. That's how you would read that. All right. So it's important to note that the percentage is first and it's to the ratio of the number of days. If oxygen is present, there's an increased likelihood of damage from radiation. This is referred to as the oxygen enhancement ratio. This is the ratio of the oxygen dose required to cause a response of an organism in an oxygen deprived environment over the radiation dose required to generate a same response under normal oxygenated conditions. Okay. Moving into effects. Cells, as they mature and become specialized, they're less sensitive to radiation. Blood cells, the radiation exposure will depress the blood count. This is caused by irradiation of the bone marrow. Lymphocytes are going to be most sensitive, and the stem cells within the bone marrow are especially radiosensitive. Tissues, the eyes, the lens of the eyes can be directly affected by radiation. This is cataractogenesis. This is considered a threshold nonlinear dose response. It's a threshold because they see that a specific amount of radiation must be exposed to the lens of the eye must be exposed to a certain amount of radiation before the biologic response occurs. Okay. The threshold for a single exposure is considered to be 0.5 gray. This is considered a late somatic effect because it takes time for the cataract to form on the eye. The lens gets damaged, but because of the way the lens is formed, there is no blood supply. So any cells that died due to radiation exposure are there as the lens itself produces cells. I'm trying to get my little marker here. So our lens is like this. This is the outer part of our eye. This is where the x-rays come in. The cells for the lens come from the center and they move out in this direction, eventually accumulating towards the back. There's no blood supply, so these dead cells never leave the lens. So they all come from the center, they go forward, and then they move around to the outside edges and come to the back where they accumulate. That takes time to happen. So any cells that are damaged from x-rays in the front, these different areas, they all have to come from that area, wherever it is that they're damaged, and move out and around towards the back. Once they pool and accumulate, then we see cataract formation, hence late somatic effect. I started x-ray school in 1991. So, 33 years, 34 years in the field. My eye appointment last year was the first mention of cataract formation on the lenses of my eyes. So again, late somatic effect. Now the threshold for a single exposure, this would be at one point, just all at once. Okay. Is 0.5 gray. But again, late somatic effect, the reduction, protection can delay that effect as well. Thyroid is said to have a linear non-threshold relationship. So we consider that the thyroid can be affected right away. Okay. It is a late somatic effect as well because it is a cumulative type thing. Um, my ex-wife worked in a room that had a radiation leak. It wasn't discovered till, you know, for a while, I think it was, but she did a lot of the fluoro in that room. And she worked in that room uh, several years, actually, you know, at least a decade and a half in that room. And she ended up um, not with thyroid cancer, but she got Graves' disease, and you know, we had to gold seed her thyroid and you know, destroy it from that. But you know, exposure for technologists is a real thing. It needs to be taken care of. Uh, that's a good question. In my experience, it's not known that fluoro would cause a headache. However, because they're using a lot of different technologies and things that produce electromagnetic fields, the you could be having a reaction to that. Also, if you're watching the fluoro when the headache starts to come about, it could be a sensitivity to screen flicker that causes that. That's a good question. I would have to, you know, next time you're doing fluoro, check and see. You know, does it happen when you're watching the monitors, or is it, you know, get on the other side of the monitor so you can't see the monitors, and see if the headache comes in. At that point, that would be the thing. If it does, you know, you may be sensitive to the refresh rate on the monitors. Breast cancer is linear, non-threshold. Most of your cancers are going to be non-threshold. That means that anything can cause. There was a study done about 25 years ago. There was a, a female, I think she was like 26 years old. She had an X-ray, chest X-ray, and they discovered through experimentation and with this one patient that X-rays in excess of 125 kV could cause a reaction in a cell, and cataractogenesis could be started at that point. And that's one of the reasons why, even though the diagnostic range in the books is 50 to 130 kV, most of your machines and most of your facilities do not go over 125 keV. The latent period for breast cancer is about 8 to 20 years, starting with skin thickening, edema, necrosis. Calcifications can also occur. With skin cancer, usually starts with the development of radiodermatitis. It's got a latent period of 5 to 10 years. Uh, Swelling, reddening, pigmentation changes, fibrosis, itching are all symptoms. For marrow, this will affect the circulation of the blood and lymph tissue. Uh, a reduction in the number of blood cells can occur due to the radiation exposure. Stem cells in the bone marrow, being especially radiosensitive, can be affected as well. With the gonads, doses as low as 100 milligray can show a response. That would be 0.1 gray. Embryo and the fetus, most sensitive during the first trimester. That's when the organs, all the stem cells are just now, they're just now being defined. We're going to start forming the different organs that are going to make up the body. Um, Prior to that, they're not. It's not a heart cell, it's not a brain cell, it's whatever. So this is the reason the first trimester is the most critical for limiting exposure. Um, we can have birth defects. Substantial amount of radiation can cause fetal death. Carcinogenesis. See, these cancer cells showcase the ability to spread to other parts of the body. They are considered a late somatic effect, and it is considered to be the most significant of all of our late stochastic effects. Early versus late, acute versus chronic. Early effects or acute effects happen all at once and are typically immediate. You want to think tissue damage. Okay, these are the most prominent symptoms here: erythema, radiodermatitis, epilation, desquamation, a depressed sperm count, and sterility, and then acute radiation syndrome. Later chronic effects are going to happen or occur after a period of time. These are going to be typically your cancers and cataracts. And Bouchon give us a really good chart and breakdown of the late tissue reactions, uh, tetragenic effects, and stochastic effects. These are our breakdowns here. Now, the deterministic tissue reactions versus the stochastic. Most of the deterministic reactions have a dose threshold, which means until you reach that amount of exposure, not likely anything's going to happen. But once you hit that threshold of exposure, as the dose increases, the probability and likelihood, as well along with the severity of damage, will increase as well. Your stochastic effects are random. They occur by chance. There's no threshold level for these things. It's going to happen or it's not going to happen. The probability of it happening increases as the dose increases. The analogy they put here is if you cross the street one time, there's a possibility of you getting hit by a car. Okay. But if you sit there and you cross the street multiple times over and over and over again and just keep repeating it, the chance of you getting hit is going to go up. And that's what a stochastic effect is. It's random. But the more exposure you get, the more likely it is that it's going to happen. Deterministic effects are threshold in nature, which means there's a certain amount of radiation that you're going to be able to absorb and be exposed to without having an effect occur at all. Hair loss, cataracts, skin injuries, etc., are more deterministic in nature. Cancers, leukemia, hereditary effects are non-threshold in nature. The slightest amount could cause an interaction or a reaction. Short-term versus long-term exposure. Short-term is usually over a short period of time. We're talking hours and days and weeks versus years. Usually due to high radiation dose. If you have develop an effect on the short term, we're looking at skin burns, hair loss, sterility as far as the reactions. Long-term exposures These are going to cause effects later in life. These are typically going to be lower in dose and spread out over a period of time. The example, cataracts, like I said, 31 years working in x-ray. Leukemia, genetic mutations, those are way off, and cancers. Moving into ARS, or acute radiation syndromes, this is going to present in four response stages. The prodromal is the immediate response. These are going to be the acute clinical symptoms, these things that are going to be what's wrong with the patient right after exposure. The latent period will be a well-being period where everything that we're not having any new symptoms, they don't seem to be getting any worse. In fact, they might even be getting better. But then over a period of time, we hit the manifest stage where we have significant signs apparent. The last stage, of course, is recovery or death, where over that period of time in the manifestation, the cells are either going to be able to repair themselves and recover, or the organism will die. So the early somatic effects, the three types of manifest illnesses that will occur with acute radiation syndrome. The first, of course, is the hematopoietic syndrome, where we get a depression in the blood count. So leukocytes, erythrocytes, all of the blood cells are starting to, they're just not reproducing enough, and we're getting a low count. They're dying. The cells are dying. They can result in death. Then we have the GI syndrome, where we get a total disruption of the GI tract. Remember, the crypt cells contained within the intestinal walls are very, very radiosensitive. Again, the integrity of the structures can be compromised. The function can be compromised and halted as well, and also can result in death. And then central nervous system syndrome, or CNS syndrome, where we've got a complete failure of the nervous system, and this will result in death. And again, because of the fact that nerve cells, brain cells are, and especially in adults, are the least radiosensitive of all, we're talking about a completely massive amount of exposure to cause the CNS syndrome. And of course, most of this information and the research came about from the World War II and the bombs that were dropped on Hiroshima and Nagasaki, and studying those effects of those people that lived during that, or lived post exposure to those bombs. This is where that information comes from, where we get all of this information from. And that will conclude the first safety lecture. Does anybody have any questions? Anything I might be able to help you with?
Hi, I have a question.
Sure.
It's actually regarding to last week's quiz. I just wanted to clarify a little bit just to
Okay.
ease my mind. So I was reviewing some of the content we had in our Lang and our Mosby books regarding, patient care, and though I feel like I was like maybe overwhelming myself with those books given the questions that they were asking, and then when I went to take the quiz, it was more straightforward questions. So I guess I just don't know what I should be expecting on the exam. I know it's like probably a mix of both, but I guess I'm a little confused.
Okay. Well, what I would do, in my mind, if you're knuckling down and preparing for the worst, and you get to the exam and it's all easy,
Hmm.
then you're thoroughly prepared.
Okay.
The flip side of that is going into it thinking it's going to be easy, not preparing sufficiently, and then getting hit with a hard question.
Fair, fair. And the comprehensive test we have on the 19th, I believe, is that going to be, isn't that, is that that's for radiation safety, or is that for both patient care and radiation safety?
Okay, so the section exams that y'all take, like you took one for patient care already, and then
Right.
you're going to do another one for safety in 2 weeks,
Okay.
procedures, etc. Those are content section specific. The
Okay.
comprehensive checkpoints are comprehensive. They're over everything. So
Okay.
it's over stuff that we haven't reviewed, but it's over stuff that you've already been exposed to and, you know, hopefully have learned.
Okay. So is that really just a way to gauge like where we're at in terms of our progress?
Yes,
Okay.
that's why there's 4 of them and they're set 2 weeks apart to see if you're gonna, you're improving overall, because ultimately we want you to be able to do good in all 4 sections.
And then what's the percentage of those towards our grade?
Um, the comprehensives 1, 2, 3, and 4 combine to make 10%.
Oh, okay, okay. So I'm not too concerned then. Gotcha.
Right,
Okay.
right. Now the final comprehensive is by itself 10%.
Alrighty. Okay.
Okay. Now the
Thank you so
section
much.
exams, they're weighted differently, but they total 30%.
Oh, okay.
So
All right.
like I said, if you want to go ahead and take like we just did safety lecture, the exam's there. If you want to take it, go ahead.
Mhm.
But if it was me, I would wait to hear both lectures before um, trying to take a section exam.
Yes,
But somebody
yes.
did recommend Rad Tech Boot Camp was helping. And yes, the comprehensives are 200 questions, and they are like mock registry exams. At least
Awesome.
that's what I believe they're supposed to be like.
Okay. All right. So then I'll just gauge off of the questions we see on those comprehensives in terms of what we should be anticipating for our registry then.
Yeah, yeah. And then, don't forget to look at the specs too. I mean, the specs
Right.
are your checklist. If you know everything about a topic in the specs, you're prepared.
I've also been watching some of Megan Paretti's videos, just to get like two different like perspectives, and I think that I'll watch that before listening to your lecture, and then kind of fill in the gaps as to where she's not covering certain topics. So that's been helpful for me.
But
Thank you
that's
so
good.
much.
I recommend any resource you can get, and also be careful with the texts. We use Lang and Mosby as well, but I mean, sometimes I've come across some bad questions and I've come across some that were actually incorrect in the book. So, when you go to look in the back for the answer or whatever, and they give an explanation, it seems to confuse even more, or it's just flat out wrong. So, if you run into anything, you have problems or whatever, don't hesitate to reach out.
Thank you so much. We'll do.
You're very welcome. Anybody else? Yes, if you have no questions, take off, bolt. Thank y'all for your time. Thank you for being here and your attention, and good luck on everything. And again, if you need me for anything, just reach out, send me a message.
Recording stopped.
Most welcome. Thank you. This was uh Miss Cooper, are you talking about the second lecture for safety or the second lecture period? Because this was the second lecture period. The second lecture for safety is next Monday. All of our lectures are going to be on Monday. Okay, good deal. Mhm.